Informative webinar that we are going to be having right now. Uh, and we'll be taking a deep dive into as to what it takes for taking a machine learning or artificial intelligence system from actionable insights to autonomous decisions. And for that, we have Professor Harshad Khadilkar joining us today. I'm just waiting for a few more attendees to join. I see that there are participants are still joining in. I can see the numbers growing. So as we wait for that, let's just run into some of the ground rules for those who may be joining us for the first time today. Please use the chat box to interact generally, or with other members, or if you have a inquisitive insight for others that you would like to share. If you have a question in particular for Professor Harshad, please use the question and answer icon so that he can be alerted and he knows that he has to answer the question. This session is being recorded live, so if you find it informative and you feel that someone missed it, you could always come back to our YouTube channel and share that link with them. And before we begin, a little bit about AID, Asian Institute of Design. We started in 2008 as Asian Institute of Gaming and Animation. This was the first institute in India to offer animation and gaming as a full-time course, as a professional course. And now we offer courses in game art, gaming, animation, and emerging technologies. All our faculties come with experience from the industry, and that is what exactly what they teach the students. And something that stands out for us as an institute are the credits that our students have been able to get in game titles as well as movie titles. Grand Theft Auto, Red Dead Redemption 2, Oscar nominated movies Jurassic Park. We are glad that our team was part of the our students were part of the VFX animation team for that. Then there is Godzilla, and there are a whole lot of titles that you could find on our website. If you would like to visit, you could also contact us on all the social medias: Facebook, Instagram, YouTube, Twitter, and LinkedIn. And now coming to the man of the hour, Professor Harshad Khadilkar. We're very grateful that he's taken out time for us during this busy schedule. Uh, he's online from Mumbai today. He joins us, and he is a scientist, a data scientist who's working with Tata Consultancy Services right now in the research division. He's also a visiting faculty at IIT Bombay, and he's himself a product of IIT Bombay 2009 batch. And he finished his PhD from MIT in 2013. And to us, he's one of the brightest minds in the field right now, as we feel. And before I go on and hand over the session to him, there's a small poll that we are running so that Professor Harshad can have a good idea of who the audience is and how deep he could go into the topic. So I would request our admin team to just trigger the poll. So here you have your question. What brings you here today? So you are an AI ML student. You are an academician involved in teaching AI ML, or you are just an AI ML enthusiast who wants to learn more, or you are an AI ML working professional. These are your four choices. You have about 15 to 20 seconds before we wrap this up, and I pass on the feedback to Professor Harshit. So I think we could close the poll now. All right. So, Professor, we have an interesting mix here. Welcome. Thanks a lot for taking out the time for us and coordinating for coming up with this very interesting topic, as well as I having seen the credit question beforehand, so I know what awaits the student. So we have about 57% of AIML enthusiasts here in the house, and rest is 14, 14, and 14, split between AIML students and academics. and AI professionals working in the field. So I think that gives
All
you.
right. Yeah, that's good.
All right. And welcome, Professor. So I would like to hand over the session to
So,
you.
shall we get going then?
Yes, we can hear you.
Yeah, yeah.
Thank you.
So, shall I share my screen? I think you are still sharing.
Yes, I have to stop my screen share. Yes.
Yeah. Okay. I hope you can see my slides. Can you see my slides, Manpreet?
Yes, yes, Professor. We can hear.
All right. So, let's get going. So, welcome everybody to this webinar. I'm going to be talking about a special subclass of machine learning algorithms, which is part of artificial intelligence. Those algorithms are called reinforcement learning algorithms, and their goal is to take you from actionable insights, which a lot of machine learning algorithms already provide, to actually taking autonomous actions on the system directly. So you're moving away from some actual human being in the loop for every action that is implemented on your systems. You are moving to an autonomous framework where you have the algorithm itself deciding what needs to be done. Now, since we are a small group, if you have any questions in between, just feel free to interrupt through the Q&A box, and I'll try to take them as we go along, or we can compile them and address them at the end as well. Okay, so today's agenda is going to be as follows. First of all, since we have a broad distribution between AIML enthusiasts and working professionals, I'll first place reinforcement learning in the context of machine learning in general, right? So that nobody is kind of left confused as to how these things work together. Then we'll go briefly into how reinforcement learning works. I won't go too deep into the mathematics because I know we have a broad audience, but I hope to give you some amount of intuition about how these algorithms work. Then we'll look at where reinforcement learning can help in the context of real world systems and where it should be avoided. And finally, I think this would be of interest to a lot of people. Talk about our real world experience at TCS in applying reinforcement learning to our client systems, uh, going from railway delay recovery to controlling lockdowns during epidemics, and also looking at problems in supply chain and so on. Right. So to give you some historical background, why these class of algorithms are called reinforcement learning, that term actually comes from the field of psychology. If you have taken any courses in psychology, you will remember that uh, from the day we are born, we actually learn to do different tasks in our life by a process known as reinforcement. So we interact with our environment, we play with toys, we think about different shapes, we touch hot objects and feel the pain of it burning your finger and so on. So all of these consequences reinforce your behavior towards things that give you good results, and on the other hand, you also have negative reinforcement towards things that actually give you bad results. Okay, so usually our actions are triggered by an what is called an antecedent stimulus, which is just an event that happens before you actually take the action, and that event gives you the context as to what action should be taken. So to give you an example, if you're fielding a cricket ball, as soon as the batsman hits the ball and you can guess the trajectory of where it is going, then your hands and legs can move towards the ball and you can field it. Right? So that's the hitting the ball is the antecedent stimulus, and then your actions take you towards the ball itself. Okay, so moving from this field of psychology into engineering, we try to replicate similar behavior, but this time instead of it being humans or animals, we are looking at reinforcing behavior in autonomous systems. So here again, we will see that the behavior is reinforced through experimentation, and where we had antecedent stimulus before in psychology, here we will have a state of the system that is detected by sensors that you have placed on the system, and your algorithm then computes the action that needs to be taken with the objective to maximize long-term rewards. Right, so this is important. Right? The fact that you are looking at long-term rewards rather than immediate gain. Okay, so to give you an example, if you have a cake sitting in your fridge, eating it right now will give you a high reward immediately, but then when you put on weight and have to diet for the next 4 weeks, then that is a pretty bad outcome in the end, right? So the algorithms that I'd be talking about are going to be the ones that exercise every day and eat a small piece of cake so that your long-term reward is maximized.
Sir, could you please turn on your video?
Yeah, actually, when I share my screen, the video goes off. I'm not sure how that happens.
All right, no problem, no problem. Okay.
Yeah, oh, hold on. So let's see if this works. Okay. So, are you able to see my video and the slides now together?
Yes, we are.
Okay, excellent. Okay. So, coming to the types of machine learning algorithms and how reinforcement learning fits into them. If you have taken any introductory level course in machine learning, or if you have read a blog or seen a video lecture, you will have seen people covering two main aspects of machine learning. The first is called supervised learning, where you have labels, which are the so called answers to every data point, and the goal is to minimize the error. Right? So your data, if they are images and you are asked to classify which images represent, have people in them, humans in them, and which ones don't, then your training data set contains the images themselves as well as the answer pertaining to each image. Right? Either the image has a human being or it doesn't have a human being. And so your goal now is to train such that your error is minimized, which means if you are given a new image, you should be able to recognize whether there is a human being in it or not. Right? So that is called supervised learning. In unsupervised learning, your goal is to actually find patterns hidden in the data. Okay, so there is no right or wrong answers here. What you're trying to find is how do individual data points actually relate to each other, which data points are close together, which ones are far away, and so on. Right? So the kind of questions you would ask of an unsupervised learning algorithm are, if I am a bank and I have seen some people defaulting on loans while others repay their loans on time, I would give it data about everybody who was defaulting on the loan, and I would ask the unsupervised learning algorithm to find out what kind of people, what attributes do they show that indicate that they are likely to default on their loan. Okay, so you give the algorithm a distance metric between two data points, and the algorithm finds hidden relationships in your data set. Reinforcement learning is actually neither supervised nor unsupervised learning. Like I mentioned earlier, the goal here is to maximize some notion of a long term reward, which means at every time step when you take an action, you get a reward, and your algorithm is trying to maximize the accumulated reward in the long term from now to infinity. Okay, so this is where reinforcement learning fits in with the other machine learning algorithms. So why is this interesting now and why has it become very popular recently? There are two key pressure points. Okay, the first is that we now know that a lot of machines are already attached to a number of sensors, and all of these sensors and therefore the machines themselves talk to each other constantly. Right? So in some parlance, this is called the Internet of Everything. Okay, so your fridge, your television, your lights are all connected to your Alexa or Google Home, and so there is a lot of data being generated from all of these different nodes in your house, and they are talking to each other, but you don't really know what to do with all this information. Okay, so perhaps it is possible in an ideal world that if you had all of this data and you knew exactly where everybody was in the house and what they were trying to do, maybe as soon as it was time for the IPL match to start, the TV would turn on, the lights would go down, and so on, right? But somebody has to actually take this decision. and there aren't enough humans in the world to look at all of this data and take the right sort of decisions. So our resources, both human as well as economic, are getting stretched, but on the other hand, a lot of data is starting to be generated. Okay, and somebody has to make sense of all of this. The second is, using reinforcement learning, we can actually teach this whole ecosystem of machines. Okay, so your appliances talking to your Alexa in your home, but hundreds or thousands of Alexas in everybody's homes talking to each other as well. So this entire ecosystem of machines can teach itself superhuman capabilities. Okay, so things and efficiencies that you would have never thought of can now be done using automated systems. And the goal is to use more data to create more efficiency. But on the other hand, because we are researchers, we also like to do things that are cool, and developing superhuman capabilities by itself is a pretty cool concept. Okay, so that's also why we do it. Small secret there. Okay, and the reason reinforcement learning has become so popular recently is because of some famous recent successes that were reported in popular media as well. Okay, so to give an example, in March 2016, Google's AlphaGo system beat the human champion in a game known as Go. Now, this is a game with a 19 cross 19 board, so 381 cells, and billions and billions of combinations of different moves that you and your opponent can take. And AlphaGo was actually able to beat the human champion in 4 games out of 5. Okay, so this in itself was a pretty impressive achievement, but look at the rate of progress, right? So going from March 2016, within 3 years, in April 2019, a company known as OpenAI built a system called OpenAI Five, which could beat teams of humans. Okay, not a single human anymore, and not working on a single board game either. Beat a team of humans in a game known as Defense of the Ancients, which is on the right side of the screen. It's actually a strategy game, and from billions of different possibilities, we now go into the realm of trillions of different possibilities and multiple people playing. And yet, this system was able to beat the team of humans pretty easily. Right? So, in 3 years, this is what the rate of progress could be. So, now people are starting to sit up and take notice of this set of algorithms. So where does this fit into the real world? It's all fine talking about games and so on, but we also need to find out what economic or practical impact these algorithms can have. And as you can imagine, a lot of things that are invented in academia finally end up in industry and make a very large difference to your life. Now, the question here is, what is it that reinforcement learning aims to do? So in this diagram, we have the system on the right. It could be anything that you're controlling. So if you are a manufacturing company, it could be your shop floor and so on. We know that the system generates a lot of data because it contains a lot of sensors, and you have your big data and IoT applications and so on. Excuse me. So you have big data and IoT sensors and so on. So these sensors already feed a lot of machine learning algorithms which do things like prediction or forecast, or they alert anything that is going wrong in the system and so on. But all of these alerts and forecasts are fed to an actual human being. And the human being takes these information points and combines them with his or her intuition or experience and decides what action should be taken on the system. The problem is, when this happens all day, 7 days a week, 365 days a year, the human being gets fatigued. And the human being also has cognitive limits. So when these things happen, the person is likely to make mistakes or not notice when something is going wrong. And this is why in reinforcement learning, our aim is not to replace the human being, not to put people out of jobs, but to let AI, artificial intelligence, do the day-to-day actions, day-to-day decision making, and move the human up into a supervisory role. Right? And so here, the human being's intuition and experience is still in play, that are no longer fatigued and they are not getting overwhelmed with information. So that is the goal of reinforcement learning. This AI block in the center is what we are trying to build. So to learn, understand what reinforcement learning does, we also need to understand what are artificial neural networks. And here I'm going to use the biological inspiration for these neural networks. The idea was that our brain, as you know, is composed of billions of neurons. These are connected to each other by what are called synapses. So each neuron receives a set of signals from its input synapses, what are called dendrites, and decides whether an electrical signal should be triggered or not. Okay, so it can communicate with its neighboring neurons an electrical signal, or it can just be silent. So when these messages are connected in very complex networks, these neurons can do pretty special things. So our entire human brain is composed of this. So the reason I'm able to talk to you over the internet and you are able to listen and understand what I'm trying to say is because these neurons have correctly connected to each other, and they have been trained as to when the electrical signals should be fired and when they should not be fired. Okay, so we are going to take this inspiration and see if we can implement something similar in a machine. So how do we model this mathematically? The idea is we now replace the biological neuron that we saw on the previous slide with an artificial neuron, which is marked by the yellow circle on your screen. Okay, so the electrical signals that are coming in through the synapses are what are marked here as x0, x1, x2, and so on. They are multiplied by weights. So depending on how much the incoming neighbor is important to this neuron, W is either more or less. And what happens inside this neuron, inside the machine, is that the signal that is coming from its neighbors is added up, and the neuron then decides whether to communicate a 0 or a 1 to its next neighbor, right? To the downstream neurons. Now, the idea is of machine learning, especially in deep learning systems, is to find out what are the best values for these weights. Okay, so W0, W1, W2, and so on for the entire set of neurons that you have connected. So, if you start with a set of sensor inputs, okay, what is the temperature of the engine right now, how much fuel flow is going through, and so on, and then you decide how much importance is to be given to each of these sensor inputs. Then you decide whether you need to run more coolant through your engine, less coolant through your engine, and so on. Okay, so the whole idea of deep learning, machine learning, and so on is to compute these weight values W0, W1, W2 for every neuron in a neural network which is inspired by an actual biological network. Okay, so at the base level, this is a very simple concept, but at the same time, like most simple concept, it can be very powerful. Yeah, and we are going to use these neural networks to make our autonomous decision making system. So how do we do that? I've converted that single neuron I was showing on the previous slide with an entire neural network here on the right hand side of your figure. So each of these little circles that you're seeing are neurons, and they're, as you can see, connected to their neighbors. And eventually you go from the state on the input side to actions on the output side. Okay, and this is an example of Super Mario, which I'm sure everybody has seen. So, what is the state of the system? What will you sense from the state of the system in this case? You would see things like where is Mario right now? Where are the possible places where Mario can get rewards? How much time is remaining in this game? Where are the enemies located right now, and so on. Right? So, all of these things are fed to this neural network, and they pass through, like I said, the weights and etc. So each of these neurons is deciding whether to tell something to its neighbor or not, and eventually at the end, this last set of neurons decides whether Mario should run forward or jump. Okay, I've kept the actions very simple right now, but you can imagine that this can be made more complex. Okay, so these actions are then decided and communicated back to the game where they are implemented. Okay, and at the end of the game, you receive the reward, which is the score that Mario has collected in this game. And that reward is used for training the neural network. By training the neural network, like I said, we are going to update the values of each weight going from one neuron to the next. Okay, so some weights will become stronger, some links will become stronger, some will become weaker. Eventually, you will come to a set of weights where Mario can finish all of his worlds in this game and win the game eventually. Okay, so that in a nutshell is the concept of reinforcement learning. So this is a mathematical representation of the same thing. We are going to look at the environment, which was the game on the previous slide, but in reality could be anything, could be a real world system that you are trying to control, or if your RL agent, the reinforcement learning agent, is still learning, then it could be a simulation of your system. You communicate the state of the system at each given time. You receive the action coming back from the reinforcement learning agent to the environment, and at the same time you also communicate the reward received at the previous time step. And the goal of this RL agent, inside which is the neural network that I showed you on the previous slide, the goal of this RL agent is to learn a set of weights, the parameters of the neural network, that maximize the sum of these rewards that are coming back from the environment over the course of time. Okay, and how we do that is pretty simple mathematics, but right now let's keep it out of scope. So where should you use this kind of concept? Okay, there is a tendency sometimes for people to start using new concepts just because they are new and they seem to work well in some environments, but they are not really useful in everything. Okay, so for reinforcement learning to be useful, you need to ask three questions and see the answers. The first question is, can you actually write a set of equations to define your system behavior? Okay, so if you can write down that my system is y is equal to x1 plus 2x2, then you can maximize y if you want to without actually needing a reinforcement learning algorithm. Okay, you can write down a mathematical formula for optimizing the system. So if you can write equations that define your system behavior, you don't need reinforcement learning. Similarly, if humans can actually explain to the computer effectively how to solve a given problem, then you will not need the computer to learn how to solve the problem. Okay, so if you have rule based algorithms, so somebody has written down a piece of code that tells the computer how to solve a problem, then you do not need to learn how to solve it. Okay, simple example is multiplication. You can actually program a machine to multiply two numbers and get it right 100% of the time. Okay, that is not something that you need to let the machine learn. On the other hand, if you have a complex problem like driving a car, you can't really write down a set of rules such that a computer will be able to drive a car. Okay, in that case, you need the computer to add some learning of its own to decide how, yeah, a car is to be driven. The third question that we need to ask is, do you have time to search for the right decisions? Okay, so if you are, say, developing the timetable for a railway network, you have probably 6 months to define the timetable. Then you don't need something that gives you approximate answers. You can actually invest the time and effort and come up with the perfect timetable. Okay, which is what the most railway networks do right now. But on the other hand, if you are in a delayed state in a railway network, in a state that you have never seen before, and you want to find out how to get back to normal operations quickly, you don't have 6 months to invest. Okay, you need to respond in probably 6 seconds. In that case, you want to use reinforcement learning type of algorithms, which can be trained earlier before all of these things happen, and then they can be used online in real time. Okay, so if the answer to all these three questions is no, then it probably means that reinforcement learning could be useful for your problem, okay, for your decision making problem. And it makes sense to implement an autonomous system that uses reinforcement learning. So, having said that, there are certain challenges when you think about implementing reinforcement learning in the real world. The first of these is that unlike games, you actually have your real world is infinite, right? So everything is connected to everything else. There is nothing that actually operates in a silo. And so if you try to train an algorithm to handle a real world system, it has to handle a system that is effectively infinite, that has a large scale. Okay, so to give you an example, that picture there is a ship being loaded with containers. And one of our tasks that we solved for a client of ours was that if a ship comes in empty and needs to be loaded by say 1500 containers, you could have a yard in your port which currently contains maybe 1,50,000 containers. Now, which 1500 containers from this pool of 1,50,000 should be selected to put on the ship is a very, very difficult problem. Okay, and at the same time, you can't spend months thinking about it because there are other ships that need to be loaded as well. Okay, so in that case, you have to use something like reinforcement learning. Another problem that we have is the complexity of the problem in itself. Okay, so if you're since we are looking to maximize long-term rewards, it essentially means that you're thinking about something that is going to happen 10, 20,000 time steps from now. And if in every time step you have a small amount of noise in your systems, a small amount of uncertainty, that uncertainty multiplies every time step, so that by the time you project or predict something 1000 time steps from now, your predictions will be very, very inaccurate. Okay, so that is something you have to handle and keep continually adjusting to. The fourth problem that we have is that we have only access to limited compute for solving these problems in real life. Okay, so to give you an example, that game that the system, the OpenAI 5 that won against humans in DOTA 2, they were collecting about 900 years worth of human experience every day. Okay, that many computers were dedicated to playing that game so that the system could learn how to play it effectively. Now, no client of ours is going to ever have that much money or time to invest to train a reinforcement learning algorithm to do something as mundane as loading a ship. Okay, so we have to make do with limited compute and at the same time deliver good results. And finally, a deal breaker for most of these algorithms and a constant criticism of machine learning or deep learning as well is that it is difficult to explain why certain outputs were given by the system in most cases. Okay, so when we design reinforcement learning algorithms, we are going to focus on keeping them explainable, which means if the client asks why did the system decide to do this, we should be able to explain to them quantitatively and justify the decisions. Okay, so these are the things we are going to keep in mind when we come to real world applications. Okay, so the first of these applications, as promised in the blurb for this talk, was recovery from railway delays. Okay, so on that map on the left, you have a depiction of the Konkan railway line, which goes from almost Bombay in the north to past Goa, almost into Mangalore in the south. Okay, now this line contains at this moment a single track that goes from north to south, where you only have passing room at stations. Okay, so you have multiple tracks at stations, but between two stations you always have a single track, which is shared by trains going south as well as the ones going north. Now, this is a difficult thing to control because if a train breaks down, say in the middle of a track, all traffic north and south of that train has to be stopped. Okay, so a small delay in operation in this kind of railway line, a single track railway line, can lead to huge disruptions in the system. And eventually, when that train is started up, all of your other trains are also delayed, and getting them back on track, is a difficult problem. At the same time, when they are trying to get back on track, you always remember that there is a single railway line, right? So they still have to share all of these resources. So this is where reinforcement learning comes into play. Okay, and the way we solved the problem of recovering from this railway delay was assuming that the delayed train, the one that had broken down, has now been moved out. and we are starting to recover all the train delays. We look at each train. Okay, so the blue icon that you see on your screen, each train looks a few stations in front and a few stations behind to find out what does the traffic situation around it look like. Okay, so it sees how many tracks are free up to the next station. Are there trains sitting at the next station? Which way are these trains heading? Are they going in your direction or are they coming towards you? And it does this a few stations forward. It also looks a few stations behind it because there might be a faster train, a Rajdhani for example, coming up behind it for which it should leave room. Right? It should not end up delaying a Rajdhani. So this kind of local information, the state that we talked about previously, is fed to a computer which decides whether this train should move to the next station or whether it should stay at the current station. Okay, so it's a very simple decision at the individual train level, but when the algorithm is properly trained, it actually knows pretty well how to move these trains forward one station at a time so that all of them get to their original timetables with as little additional delay as possible. So this is one of the powerful ways in which reinforcement learning can help you, because there is no clear optimization based method that can solve this. Right? So you could have 80, 90, 100 trains running in your railway line at a given time, and if you have to compute stop go decisions for all of them together, it will take hours, which you can't afford to wait. So this is why something lightweight that has been already trained previously and can now be used directly is of use. Okay, and for anybody who is technically inclined and wants to read this approach in detail, there is a paper referred to at the bottom of the slide which you can look up. A second and very topical case right now is this thorny idea of doing district-wide lockdowns. Right? In the COVID scenario recently, we had this nationwide lockdown, and people were wondering whether if you could do something more locally oriented at the district level, so that districts that are not having too many COVID patients can be opened up, some economic activity can be started, while others where the disease is spreading very fast can be closed down. Okay, and so because we have about 700 districts in India, on every day you have to decide which of these 700 districts needs to be locked down and which ones can be kept open, so that you can balance the health risk, the health cost that is imposed by COVID patients, and the economic activity as well. So both of these things have to be balanced. And so, similar to the previous railway scheduling example, we look at each district and its neighbors and the districts that it is connected to strongly. So, for example, Bombay is connected very strongly to Delhi, Kolkata, and Chennai. So, you don't want to look at just the local area around Bombay to decide whether it should be kept open or locked down. You want to look at its strongest neighbors as well. Right? So, all of this information is collected for every district, and the rate of growth of COVID patients, how many people are recovering, how many have already recovered. All of these context variables are given to the algorithm, which then decides whether to keep the district open or whether to lock it down. Okay, and so that people's lives are not disrupted too much, we don't do this every day, we do it once a week. So this is only a simulation based study right now. It is not implemented in the real world. But our hope is that if next time something like this happens, we should be able to help the government do a more precise control of lockdowns around the country. And finally, a third, somewhat lighter case study is how do we reduce the cost of replenishment in a retail supply chain. Okay, so replenishment is the process of supplying the stores, which are the last nodes in your supply chain, with products that people come and buy from the store. Okay, these products are sourced many steps before this, directly from a farm or from a manufacturing unit. They are brought to a large regional warehouse that is owned by the retailer. From the regional warehouses, they are sent to smaller local warehouses, and from the local warehouses, the products are sent to the stores. And the goal of this entire supply chain is to ensure that the products, when people walk into the store, all of the products that they want are stocked in the store. At the same time, if you have things, perishable products like tomatoes or onions, you are not stocking so much that the products are going to waste. Okay, so there is a balance at play here. Another level of complexity is the fact that these processes, the arrows that you're seeing, happen at different time intervals. Okay, so the stores are getting restocked maybe once a day from the local warehouse, but the local warehouse is only getting stock from the regional warehouse once a week, and the regional warehouse actually has to think maybe 6 months in advance as to what contracts to set up with the vendors. Okay, so at all of these different time scales, if you want to take decisions that optimize the flow of products through your supply chain, then again there is no hope for a traditional optimization type of engineering. So we have come up with a multi-agent reinforcement learning algorithm. This is a slightly advanced version of reinforcement learning, where each of these stores in your picture and each of the warehouses as well as the transportation agents, trucks and so on, are their own reinforcement learning agents. Okay, so each of them is learning on its own how to best work with its neighbors. Okay, so the regional warehouse is figuring out what contracts to set up with vendors and how much to send to the local warehouses. The local warehouses are figuring out how much to ask from regional warehouses and how much to send to stores, and so on and so forth. Okay, and all of these agents are getting their own rewards, they are getting their own states, and they are deciding their own actions. And eventually we come up with a solution, a policy that optimizes the cost of this entire supply chain just by doing individual local based optimization. Okay, so slightly more advanced, but I just wanted to give you a flavor of the fact that reinforcement learning does not stop with just one agent. You can have hundreds and thousands of agents working together. And if we hark back to the start of the presentation, we were talking about an ecosystem of machines becoming superhuman capable. This is exactly what it is. Okay, it's an ecosystem of stores, warehouses, and transportation agents working together to deliver superhumanly low costs in your supply chain. And this is a product that is already out there. It is marketed as TCS Optumera. So the takeaways from this application experience are: first of all, because you need to train the reinforcement learning agent before you deploy it in a real world system, you have to build a simulation of your real world system. And because, like I said, real world systems have connections to everything else, are essentially infinite, they are very difficult to simulate effectively. Okay, so getting that simulation right so that the reinforcement learning agent can be trained is key to the success of RL. First of all, you have to find data sets that help you model the system, understand how the system behaves. You have to design what is called a counterfactual reasoning environment, which means not only do you need historical data of how the system operated, but if you ask it a counterfactual question, in the sense, if instead of this I had done that, what would have happened, the simulation should be able to answer it. Okay, so if instead of 10 boxes of cereal I had sent 20 boxes of cereal to this store, what would have happened? That kind of answer should be queried from the simulation. Obviously, we need domain experts, people who have worked in this area for 10, 20 plus years, to help us guide the simulator as well as help us when something goes wrong during training. So again, there is a key role to be played by human beings in all of this framework, and to try and break down the complexity of the problem into a sequence of smaller manageable tasks. Okay, you will have seen this repeated in all of the examples I gave you, right? So initially there was the railway rescheduling where decisions to stop or go were given at a train level, individual train level. In the lockdown problem, again, each individual district was deciding whether to lock down or to remain open. And in the supply chain, each node was learning on its own how to coordinate with its neighbors. Okay, we want to define goals that can be achieved by repeatedly performing the same smaller tasks. So if you are moving trains back to their original timetable, as long as each train keeps deciding whether to go or stop at every station, eventually it comes back to its original timetable if the algorithm has been trained properly. And remember that reinforcement learning should not be used everywhere and anywhere. There are certain specific questions that you should ask before you decide to use it. Right? And always keep in mind that algorithms in 10, 20, 30 years, their existing knowledge, the heuristics that they have developed, the thumb rules they have developed, should be used to help your algorithm learn faster. Okay, and finally, a small lighter note that I want to leave you with is this problem of specification gaming by the algorithm. Okay, so whatever reward you decide to give the system is what it tries to maximize, and sometimes if you design the reward badly, the system can learn the wrong things. Okay, so for example, in reinforcement learning, I read a paper about this. There was a team that was trying to train a robotic arm to pick up a box, a parcel, and put it on top of a cross which was placed on a stool. Okay, and so whenever the parcel was placed on the cross, it would get a reward. Now, what happened? The robotic arm accidentally knocked over the stool, and the cross fell on the floor. And the system put the box on top of the cross, which was now lying on the floor. Okay, and because it got a reward for this, the reward was only given when the box was placed on the cross. The system actually learned, the algorithm actually learned to knock the stool over and then put the box down. Okay, so this is an example where the reward was badly designed and therefore the system learned to game that reward. Okay, so that is essentially it. Let's take questions, Manpreet, or if people have already sent any questions in Q&A, we can address those. Thanks.
Yes. Hi, Professor. There are most questions, I think, because of the value, I think they find the session very valuable. Wanted to know if they would be receiving certificates for it. Yes, participation certificates will be emailed to you within 3 days on the email ID issued. And but this does not certify you on the magnetic concept. So it's only participation document. And other than that, what
So there are a couple of questions in this, right? So one is for additional resources or references, there are actually two or three very nice online courses which you can take. One is by Professor Balaraman Ravindran at IIT Madras. So if you just Google for his name and reinforcement learning, you will get a course, online course videos which are freely available. There is another course which again is freely available from the University of California at Berkeley. Okay, both those courses are worth doing if you're really interested. And then in terms of computational power, it depends on how much how complex your final model ends up being. So you could run these algorithms from anything as small as your laptop up to a large supercomputer. Okay, in terms of using CNNs instead of RL, so CNNs and RLs are not uh, you know options that you have to do one or the other. People actually use CNN inputs for reinforcement learning also. So reinforcement learning is a set of algorithms that help you learn how to take decisions autonomously, whereas convolutional neural networks are a way of handling inputs that are coming in as text or audio or videos or images. Okay, so you can have neural networks based on CNNs as well as other things like LSTMs, which are used for reinforcement learning. I guess those are the main questions. Okay, which model-based reinforcement learning algorithm is suitable for real-time robotics? Again, it completely depends on what your task is, what kind of inputs you have available, and so on. So if you have a more specific question, you can find the right answer, or you can email me what your problem is, and I can help you find it. For computer aided drug discovery, is RL an option? Yes, people already do it. I know there are projects happening in Novartis and at least one other company, I forget which one, which is doing drug discovery using reinforcement learning. So, definitely possible to do. Okay. I guess, Manpreet, okay, there's one more question. Will AI take over humans? See, this is a question that comes up a lot. Okay, and you have to know that artificial intelligence does not have motivation. Okay, so when you talk about taking over humans, if you're talking about the Terminator kind of scenarios where it rules humans, only humans are diabolical enough to want to dominate other beings. Okay, artificial intelligence or machines have no intrinsic motivation, so they just do the task that they are given. Python libraries, we use basic Python libraries, Keras, TensorFlow, PyTorch itself. Okay, so the implementation of reinforcement learning is very much in the same form as you have for deep learning libraries. So you don't need anything different for RL. What else? Okay, Manpreet, I guess that's about it for the questions.
Right. I think a couple of them there was there like how can we improve RI learning agent training? Uh, and are there any Python libraries that help improve RL?
Yeah, that I talked about, right? That we use the same ones as deep learning. So there are no new libraries. So improve RL learning agent training, I'm not sure. It's a somewhat vague question. So if you can make that more precise, I can answer it.
Uh, I think we'll wrap it up here because I know you have another call at 2:30.
Yes, yes.
Have a hard stop today, so we can't extend. Generally, our webinars tend to extend because, as you can see, the questions tend to go towards the end. So it's
Yes, yes.
but it
Yeah,
was
unfortunately, in weekdays it becomes very hard to,
uh,
take out more time.
completely understand, Professor. And
Yeah,
thanks a lot for taking out the time. It was wonderful.
sure.
And going by the questions, I can see that you piqued the interest of a lot of people, and I think they are going to come follow you on your journey from there, perhaps
Sure.
for new answers. And thank you once again. It is such a pleasure, and
Thank you.
from on behalf of Asian Institute of Design, we very grateful uh, for you to take the time for us, and we hope to have you back soon with probably another interesting subject as well, and shed more light. Uh, Thank you. Thanks a lot. Wrap it up.
Sure. Happy to be here. Thanks for inviting me. Thanks.
Thank
Bye.
And thanks for all those who have attended. You will, as explained, we will send the certificate within 3 days. Thank you. We're closing it here. Thanks for attending. Bye bye.